To fight Alzheimer's disease by studying brains with multi-beam scanning electron microscope, you need proper signal integrity. To understand the universe by looking at it through a radio telescope, you need proper signal integrity. To protect chips against cyber by making them all different, you need proper signal integrity. Just to get an idea for myself, who in this audience would typically manage such a project? Who are managing this project? Okay, so who would architect something like that? Okay, and who would make the PCB layout? Okay, okay, one third, more or less. So this is about you. But the question is, should you worry about signal integrity? And how to worry in a cost-effective way? And at best, how to avoid problems altogether? Willkommen, bienvenue, welcome to everybody. Thank you for coming all the way to Gouda, the Netherlands, even for some coming from abroad. My name is Sjoerd Op. I am confident that today's talks and drinks will answer those and many more questions. I will present the program in a moment, but let's first take 15 minutes to start at the beginning. Because what is signal integrity? And why is it hard? And let me illustrate it with one signal integrity problem. It's a problem that occupies me already since a while. Since primary school, actually.
As a boy, I was intrigued by the fact that the light bulb would switch on immediately when you flick the switch. However hard I tried, I could not measure any delay between the flicking of the switch and the turning on of the light. In high school, this was confirmed. Wires carried the same current and voltage everywhere along the line. But at the same time, relativity taught that no information could travel faster than the speed of light.
A paradox. And this paradox points us to this one problem I would like to illustrate now. And the problem is called reflections. We move from light bulbs and switches to our world of PCBs and ohm meters. We have a trace and a resistor. What happens when we turn on the ohm meter? A voltage is applied, current flows, the ohm meter does the math and displays the resistance. But now the paradox. This resistance value is a piece of information which travels a certain distance. So remember the finite speed of information? This must take a certain amount of time. What if the line would be infinite? And I would turn on the ohm meter. What would happen now? Turns out that such a line actually is an infinite distributed capacitance. And when you turn on the ohm meter, it's charged. Fortunately, not all at once, because the current is impeded by a distributed inductance along the line. And as it turns out, this is a constant current. While the charge front propagates, there's a constant current flowing at the beginning, and this is displayed by the ohm meter. And this number is characteristic for the ratio between the capacitance and the inductance, or between the electric and the magnetic fields. And this ratio is called the characteristic impedance. And it depends on the electric and the magnetic fields in the cross-section of this homogeneous line. Now notice that from an ohm meter's point of view, it cannot tell the difference between an infinite line of 100 ohms characteristic impedance or a single resistor of 100 ohms. This is important to remember. Now let's take the finite trace again. So if we change the cross-section, you would have a different characteristic impedance. now we have this 150 ohms resistor again, and a trace of 100 ohm characteristic impedance. What will happen now when we turn on the ohm meter? We will look at the voltage along the line throughout time. Turn on the ohm meter. We see the charge front propagate. The current is flowing that belongs to 100 ohms. And then, hey, there's some kind of surprise traveling back. Because it turned out that the charge front that was propagating, the current, induces a different voltage across 150 ohms, a higher voltage than across this 100 ohms. The surprise travels back to the ohm meter and now displays the correct value. This kind of surprises are called reflections. You still remember that we can also replace a resistor by an infinite trace with the same characteristic impedance? Let's do that. And as you will see, from the ohm meter's point of view, nothing has changed. This is the major takeaway from this crash course. Changes in characteristic impedance cause reflections. Now let's go from infinite traces to something even more realistic, PCBs, high-speed digital signals. For example, a PCI 5 transmitter, a trace which needs to neck down here to mounting holes and a receiver. And we will probe the signal as it arrives at the receiver, and we will also look at the voltage along the line as we just did. What will happen now? Because we have here two transitions, two changes of the cross-section. So we expect reflections at both interfaces, something like that. Let's have a look. We transmit a single edge. We see one reflection going back, another one. Hey, what's going on here? We see one edge going towards the receiver, but also a second edge. Let's see if they arrive. Here's the first edge, second edge, and there's even the third, very tiny edge. Now the question, of course, is this a problem? Let's look at something more close to real life. We are going to transmit random bits. Now you can see it becomes a complete chaos over here. But in the end, that's not what we're interested in. We're interested in the signal at the receiver. And it looks still okay. You can discern ones and zeros from each other. It's distorted a little bit, but again, maybe it's not a big deal. How to know? And to answer that question, we need to look at the rise time. Because in this case, we had quite a short rise time, which corresponds to short rise length. Let's look at a slow edge. This one goes really slow, and because the velocity isn't changed, the rise length is much longer. The rise time is much longer as well. And here, the different echoes that you just saw are molded into each other. You cannot tell them apart anymore. But in the case of, so here we will not really have a problem because the rise length is big with respect to the length of the discontinuity. But if we go back to a fast edge with a short rise time and a short rise length, that is short with respect to the length of the discontinuity, you will probably have problems. But let's dig deeper still. When is short too short? For example, what if the discontinuity length is equal to the rise length? Will you have problems or not? And the answer depends on the application quite a bit. So who here is mostly involved in digital applications? Okay, I would say 50%, something like that. Analog? Okay, also 50-50. Nice. That was a question we just asked John, whether everything would be about digital. Apparently not. So for the digital case, the answer is easier. There's a rule of thumb that if the length of the discontinuity is 1/5 of the rise length, that's more or less the crossover point where you need to start worrying. However, in the analog case, it's much harder to tell, because if you have very stringent criteria on this acceptable distortion, then maybe you should start worrying much earlier. So yeah, I'm sorry, do not have an answer for the analog people straight away. You have a question?
I would say, does it also depend on the amount of discontinuity? That's the strength of discontinuity. Not only that ratio. I mean, if you have a very large discontinuity,
yeah,
you will also see it.
Definitely. So the question was, does it only depend on the length, or does it also somehow depend on the magnitude of the discontinuity? Maybe a small change of the cross-section still acceptable, whereas a very big change in cross-section, however short in propagation length, may be even worse. And that's a good question. So it is a rule of thumb, and I think it holds for modest changes. But if you would have, for example, I don't know, 25 ohm for however short, but with respect to the rise time, would still deserve some more attention. Good question, thank you. Please do not hesitate to interrupt me. You can also ask questions at the end. Okay, so this was still quite a simple example. Let's look at something more complex and real life. Sometimes in differential digital links, you need to accommodate for different bias voltages at either end. And for that, you incorporate coupling capacitors in series with the link. But the solder pads of those coupling capacitors are wider, so you locally have excess capacitance and lower characteristic impedance. So you will get reflections. And one way to get rid of those reflections is to make a cutout in the ground plane just underneath. The question is, how big should this cutout be? One approach, one taken in the example I cite here for 100 gigabit per second, required electromagnetic simulations. But in order for this simulation to be realistic, you also need to know what's going on inside the capacitor. And that, of course, the structure is the trade secret of the manufacturer of the capacitor. So in this particular case, X-ray cross-sectioning was used to count the number of plates, to extract material parameters, and to create a proper model. They also compared whether this was actually necessary by using a simplified capacitor model, and in this case at 100 gigabit per second, it did matter. But the rabbit hole is deeper still, because in simulation, those capacitors are perfectly aligned above the cutouts. But you know that the PCB is the result of a lamination process where things need to be aligned, and it's never perfect. Turns out that a realistic offset between the layers can make the current distribution asymmetric in a way that you get even more reflection than you would have had without cutouts. There is a solution. There are smart cutouts that are robust in the sense that if you have some offset, the current that you win on this side, you lose it on the other, and on average to first order, you're not sensitive to these kind of offset problems. But this needs considerable thinking time. Now, this was just about reflections, not about crosstalk and loss. These were just a few examples. And I think you have seen enough. Signal integrity is hard. So I think there's enough to discuss today. So together, let's learn everything we can. Thank you.